Okay, let's unpack this. You work with data, right? Chances are a huge chunk of it lives in tables. You know, spreadsheets, databases, all of it.
Exactly, fundamental stuff.
Yeah, tabular data is key for, well, pretty much everything. But for the longest time, if you wanted to build a predictive model on that data, the kings of the castle weren't those fancy deep learning models.
No, definitely not.
It was the gradient boosting decision trees, your XG boosts, your cat boosts. They just worked better on that kind of data. Much better than the deep nets that were totally crushing it in images and text.
And that's really been the puzzle, hasn't it? Deep learning loves structure, pixels in a grid, words in sequence.
Right.
Tabular data, it's often messy, heterogeneous, sparse sometimes. GBDTs has had these built-in ways to handle that kind of chaos.
But here's the thing, the catch that's become super obvious in the real world, tables aren't just neat numbers and categories anymore.
Yep.
They often have these rich, unstructured text fields mixed in. Think about, like, patient records in a hospital. You've got age, department, sure, but also those critical free text doctor's notes.
Or product reviews next to sales figures in e-commerce data. That text is packed with vital information.
Exactly. And this is where the traditional methods, even those powerful GBDTs, and honestly a lot of the early attempts at deep learning for tables, they just kind of hit a wall.
They really did. They tend to treat text features pretty poorly, usually by boiling them down to static embeddings.
Static embeddings, like what, a fixed vector representation?
Yeah, calculated once, maybe from some big generic model, and then frozen in place. It can't adapt.
So it's like taking a whole, I don't know, complex report and just giving it one score for medicalness or something. You lose all the nuance.
Precisely. A static embedding for a note like mild chest discomfort.
Yeah.
It might tell the model it's medical text, okay, but it won't learn why that specific phrase is so important for predicting, say, released versus hospitalized in this specific data set.
The model can't tune its understanding of the text based on what it's actually trying to predict.
Exactly. It's stuck with that generic meaning.
And that leads us right into the challenge for this deep dive. How do we finally make deep learning not just, keep up, but actually excel at tabular data, especially when you've got that critical text information mixed in?
Which brings us nicely to this new model discussed in the source material we looked at. It's designed specifically for this problem. It's called TabSTAR.
TabSTAR, okay. The paper calls it a foundation tabular model with semantically target-aware representations. That's a mouthful.
It is, but the name actually gives you clues. Foundation Tabular Model aims to work across many tables. Semantically target-aware, it understands meaning and connects it to the prediction goal.
Gotcha. So it's trying to bridge that gap. Use the power of deep learning, especially from language models, but make it work for tables with text.
That's the goal. And our mission today is to, well, cut through that complexity. We're going to dive deep into the source material, figure out what TabSTAR really is, understand the core ideas, see how it actually performed.
And pull out the key insights, right? Get everyone up to speed.
Exactly.
Okay, so let's start with the baseline. You mentioned GBDTs like XGBoost and CatBoost dominated. Why were they so good at the typical tabular mess?
Well, they're just inherently robust.
Yeah.
Different data types, weird distributions, missing values. GBDTs handle it. They build these decision trees that capture complex interactions between features.
Without you having to manually figure out all those interactions first.
Right. And they don't usually need careful feature scaling, which can be a real headache for deep learning models. Their structure just naturally fits that heterogeneous table format.
And deep learning, built for those neat grids and sequences, just tripped over that mix of stuff, the lack of obvious structure.
Pretty much. It was like trying to fit a square peg in a round hole. And that problem gets way worse when you add text.
Because of the static embeddings we talked about.
Exactly. If you're just using a fixed vector, you're not letting the model truly learn how the text's meaning actually relates to the prediction task. In that patient example, mild chest discomfort versus, say, reports episodes of vertigo.
Very different implications for being released or hospitalized.
Hugely different. But if they're both just generic medical text vectors, the model might struggle to see that crucial difference effectively.
Okay, so TabSTAR is the proposed fix. What are the big, core innovations they talk about in the paper to tackle this?
There are two main ideas that really stand out. First is the unfrozen text encoder.
Unfrozen, so not static. You're letting it change.
Precisely. They start with a good pre-trained text encoder. The paper mentions using something like E5 small v2. But, and this is key, they keep part of that encoder, some of its layers, unfrozen.
Ah,
This means the encoder's parameters can actually be adjusted or fine-tuned while training the whole TabSTAR model on the specific table.
so the text part learns what matters in the text for this specific prediction task.
You got it. It learns to focus on the text patterns most relevant to predicting hospitalized versus released, for instance. It adapts.
That makes a ton of sense. Okay, what's the second big idea? You called it target-aware tokens? That sounds different.
It really is. It's quite novel for tabular learning, actually. Instead of just feeding in the features and asking the model, okay, predict the outcome for classification tasks, they do something clever. They take the possible outcomes themselves.
Like released and hospitalized.
Exactly those. They turn them into special input tokens and feed them into the model alongside all the regular feature data.
Wait, hold on. So the model sees the features and the potential answers like all at the same time from the start?
Yes. It gives the model explicit context about what it's trying to choose between right from the beginning. The embeddings for the features can interact directly with the embedding for the release token and the embedding for the hospitalized token.
How does that help?
Well, those interactions happening inside the model help it build representations that are directly focused on figuring out the likelihood of each specific outcome. It's not just outputting a class, it's reasoning about the given classes.
That's clever, grounding the prediction explicitly. And the paper mentioned this helps make it a foundation model, helps with parameter sharing.
Absolute critical point, because you're using these generic target tokens that just represent the concept of the class values, the core prediction mechanism, how the model looks at the final embeddings of those target tokens can be the same across different classification tasks.
Regardless of how many classes or what they're called.
Exactly. You don't need a unique output layer designed for released hospitalized and another for fraud not fraud. It avoids needing dataset-specific output heads, which is a huge barrier if you want one model pre-trained to work on many different tables.
Okay, I think I'm grasping the why. The unfrozen encoder lets text adapt. The target tokens give context and allow sharing. Now the how. How does TabSTAR actually chew on a row of data? The paper had that verbalization step.
All right, let's walk through the pipeline for a single row. It starts with verbalization. Everything gets turned into a standard format, mostly text strings.
Everything, even numbers.
Yep. Numerical features like age 45 get processed in two ways. They keep the standardized numerical value, maybe a z-score like 0.27, but they also generate a semantic description, something like age, 40-50, quantile, 50-60%.
Ah, so it gets context, like where it falls in the distribution.
Exactly. And then categorical features like department, cardiology, or the actual text features like report, mild chest discomfort, they just become descriptive text strings.
Okay, simple enough. What about the target values, those target-aware tokens?
For classification, the possible target values, hospitalized and released, are also verbalized, maybe as target, decision, hospitalized, and target, decision, released. And here's the kicker. These verbalizations for all potential outcomes get included in the input sequence for every single row being processed.
Got it. So for every patient, the input includes their info and the text for hospitalized and the text for released.
Correct. Now you have this sequence of text strings and maybe some raw numbers. Next step, encoding.
Turning it all into vectors.
Right. These verbalized strings and numerical values get turned into high-dimensional vectors, or embeddings. This is where that unfrozen text encoder does its main work on the text parts. The numerical values get projected into that same embedding space, too.
So now everything's speaking the same vector language.
Exactly. Then comes fusion. This is mainly for features that had both a numerical part and a semantic description, like our age example.
Right, the z-score and the 40-50 quantile text.
Yeah. Their separate embeddings are combined, maybe using a small transformer layer, into a single richer embedding that captures both the precise value and the broader context.
Okay, so after fusion, we've got a set of embeddings, one for each input feature and one for each possible target outcome token.
Correct, and all of these embeddings are fed into the main interaction module. This is basically a standard transformer encoder.
Like the ones used in language models.
Very similar. These embeddings are treated like tokens in a sequence. They all attend to each other using self-attention. Importantly, the order you feed the feature embeddings in doesn't matter, which is good for tabular data, where column order often isn't meaningful.
So they all talk to each other. The features talk to features, features talk to the target tokens.
And the target tokens talk to the features and even each other. The transformer learns all these complex relationships, how features relate to each other, and crucially, how they collectively support or contradict each of the possible target outcomes represented by those target tokens.
It sounds like the features are presenting their case, and the target tokens are listening and building up evidence for themselves based on that input.
That's a pretty good analogy, yeah. And finally, prediction. The transformer processes everything and would look at the final contextualized embeddings that come out for the target-aware tokens.
So the embedding for the release token and the one for the hospitalized token after they've gone through the interaction.
Exactly. Those specific output embeddings are fed into a small shared classification head. It just predicts scores based on those embeddings. Then you usually apply softmax to get the final probabilities for each class.
And because that final prediction step only looks at the target token embeddings, not the specific class names, that little prediction head can be reused across totally different classification problems.
That's the key to the foundation model aspect for classification.
Okay, I think I've got the flow conceptually: verbalize, encode, fuse, interact via transformer, predict using the target token outputs. But, the proof is in the pudding. How did it actually do? Did it work?
Right. The experiments, the researchers really put it through its paces. They pre-trained TabSTAR on a big collection, 350 tabular datasets, and they noted they had to curate some of these themselves to make sure they actually included text, because good text-rich tabular benchmarks are apparently scarce.
Yeah. Interesting point in itself. And then they tested it.
Yeah, they evaluated on a separate benchmark of 50 diverse datasets.
Yeah.
They do acknowledge this benchmark leans a bit more towards regression and high cardinality features rather than text,
Yeah.
but it's a start.
Okay, and the results, what's the headline?
The headline, especially for classification, is pretty striking. TabSTAR was the clear winner. It set a new state-of-the-art performance for classification tasks.
Better than GBDTs, better than other deep learning attempts.
Yes, significantly better than both traditional GBDTs and other leading tabular foundation models like CAB-PFN, particularly when text was involved. It seems like the design choices really paid off for classification.
So the core goal, cracking the text and tabular problem for deep learning, they seem to have actually achieved it, at least for classification tasks.
It looks that way based on these results. I mean, look at the numbers they reported. In the setting with limited training data per task, like 10,000 examples,
Yeah.
TabSTAR got a normalized score around 0.809. The next best foundation model, TabPFN v2, was 0.783, and the GBDTs were hovering around 0.75. So a noticeable edge.
Okay, that's decent, but you said it got better.
Right. When they let the models fine-tune with unlimited data from the training set, basically allowing them to really learn the task, well, the gap widened dramatically. TabSTAR Unlimited hit a normalized score of 0.874.
Wow. And the others?
Cat Boost, even tuned and with unlimited data, was down to 0.734. That's not just winning. That's a pretty decisive leap forward in that unlimited data setting.
Okay, that's impressive for classification. What about regression? Predicting continuous numbers?
Yeah, regression tells a different story. TabSTAR was competitive, decent performance, especially with limited data where it was strong. But it did not set a new state-of-the-art there.
Ah, so who was better?
The GBDTs. They still performed better overall on the regression tasks in this benchmark, even outperformed TabPFN v2 in some scenarios. While TabSTAR did improve with more data in the unlimited setting, it didn't close the gap with the top GBDTs for regression.
That's really interesting. Dominant in classification, especially with text, but still lagging GBDTs in regression. Any thoughts on why that might be? Is it about predicting categories versus numbers, or?
That's a great question, and the paper doesn't give a definitive answer, but you can speculate. Maybe those innovations, like the target-aware tokens, are just inherently more suited to distinguishing between discrete classes, which is classification.
As opposed to pinpointing a value on a continuous scale.
Right. Or perhaps the way TabSTAR currently handles numerical features in their interactions, even with a verbalization, isn't quite capturing the complex numerical relationships that GBDTs are so good at finding through their tree structures. It's an area for future work, for sure.
Makes sense. Okay, so given how well it did in classification, the researchers must have dug into why, right? What parts of the design really made the difference? The secret sauce.
They did. They ran ablation studies, basically, systematically breaking parts of the model or changing settings to see what happens to performance.
What did they find?
Well, first, confirming our earlier discussion. The unfrozen text encoder is absolutely crucial.
Can't just use static ones.
Nope. Performance was way worse when they used completely frozen static embeddings. That was their Q1 analysis. Unfreezing even just one layer of the text encoder helped, but they found the sweet spot was tuning about half the layers 6 in their setup. It really proves that adapting the text understanding to the specific task is vital.
So you need that fine-tuning. Got it. What
Right.
else?
Second big takeaway, the power of pre-training, Q2 of the paper.
Hmm.
Pre-training TabSTAR on that large collection of 350 diverse data sets before fine-tuning on a specific task. Absolutely critical.
It needs to see a lot of tables first.
Yes, and they showed a clear scaling relationship. The more data sets they used for pre-training, going from 0 up to 256 of their chart, the better the model performed on the downstream benchmark tasks. It really behaves like a foundation model should, learning generalizable patterns from broad data.
That fits the whole foundation model paradigm. Learn general stuff, then specialize. What about handling the numbers?
That mattered too. Their analysis, Q3, looked at handling numerical features. Their specific strategy, using both the standardized numerical value and that semantic verbalization with quantile info, age, 40, 50, quantile 50, 60%, performed better than simpler approaches.
Like just using the feature name or just the simple bin description?
Exactly. Better than those. It suggests that providing that richer context, bridging the numerical world and the text world for the language model core, is beneficial.
Okay, so summing up the analysis. Unfreeze the text encoder, pre-train on lots of diverse tables, and handle numerical features with both value and semantic context. Those seem to be the keys to its classification success.
That's what the evidence points to.
So the big picture here is, TabSTAR represents a really significant step forward for deep learning on tabular data. It set a new benchmark for classification, especially when text is in the mix.
Yeah, it achieved this by cleverly integrating ideas from language models, that adaptable text encoding, and the novel target-aware tokens providing context.
And this really matters because it shows deep learning can potentially beat the reigning champs, the GBDTs, in these crucial areas. It helps unlock the value hidden in all that text sitting inside tables in places like, well, healthcare, finance, retail.
Huge potential impact there.
Now, they were upfront about limitations too, as you mentioned earlier. Regression performance needs work.
Right, it's not soda there.
And it can apparently get memory hungry if you have tables with hundreds and hundreds of features.
Yeah, transformers can have quadratic scaling issues with sequence length, and if each feature becomes a token.
And it's probably more computationally heavy than running a GBDT right now.
Generally, yes. Training and fine-tuning these models takes more compute. Those are definitely current challenges.
But the future directions they point to sound promising. What did they mention?
Well, the obvious one is scaling up bigger TabSTAR models, pre-trained on even more diverse tabular data. See if those scaling laws continue.
Lisa.
They also talk about integrating more world knowledge, maybe by leveraging larger general-purpose LLMs in smarter ways. Perhaps to improve how numerical data is understood, or to inject external context relevant to the table's domain.
Using an LLM's knowledge to enrich the tabular reasoning.
Potentially. And another important point they make is about improving benchmarking itself. They highlighted the need for better, uncontaminated benchmarks, especially for text-rich tables, and they're releasing versions of their models trained without seeing certain common test sets to help the community evaluate fairly.
That's a solid contribution back to the research field. Okay, so the core takeaway really feels like deep learning is finally making serious inroads into tabular data, especially for classification where text plays a big role, by borrowing and adapting powerful techniques from the language domain.
It's definitely shifted the landscape and shown a promising path forward. It's not just about images and text anymore for deep learning.
Right. And thinking about that future, if scaling TabSTAR further with more data keeps improving performance, and you combine that with the sheer amount of world knowledge packed into today's huge language models, what kind of really complex, text-heavy, tabular problems could that unlock down the line? I mean, could we see breakthroughs we haven't even really conceived of yet, maybe in scientific discovery, like connecting messy lab notes with experimental data tables? Or truly personalized medicine, linking detailed doctor's notes with genomic tables in ways we can't currently manage?
That's a really powerful thought. The convergence of deep language understanding and scalable tabular data processing. It definitely opens up avenues that seemed blocked before. We might just be scratching the surface of what's possible there.